The next speaker in our series is Virginia Vassilevska Williams. She's also from MIT Computer Science and Artificial Intelligence Lab. And you see her subject on the screen. Please go ahead.
Thank you. Thank you for inviting me. I'm really excited to be here. And thank you for staying for one of the later talks today. So I will be talking about fine-grained algorithms and complexities. So to begin, let me talk about algorithms. So what is the main topic of algorithms? If you look at all these books over here, they will tell you that the main topic is how fast can we solve fundamental problems in the worst case. Okay, so I need to parse this for you. So maybe you haven't taken an algorithms class before. So here's what we mean by this. We study various functions which are computable. They take bit strings and output bit strings. And we fix a reasonable model of computation, such as a Turing machine or a random access machine. And this model of computation defines various operations that you can do in constant time, for example, like XOR of bits or multiplications of small integers and so on. And then we study algorithms, which are basically programs implemented in this machine model. And these algorithms compute our function f so that for every bit string of length n, let's say it's x, they output f of x. And what we want is to understand how good these algorithms are. And what is the quality of an algorithm? Well, for a particular input, the quality of the algorithm is its running time, which is the number of basic operations that the algorithm needs to compute f of x given x. Now, for every input size n, we are interested in the worst case running time, which is the maximum overall possible inputs of length n of the running time on that input. And we want to get a handle on the asymptotic behavior of this running time, and in particular the asymptotic behavior of that running time for the best algorithm. Now, for the problem, right? So what kind of a running time do we want? The golden grail for most problems is to get a linear time algorithm whose growth is order n on inputs of size n. So why is this desirable? Well, for most of the interesting problems that we consider, you have to at least read the input. And the input has n bits, and order n is asymptotically optimal. Now, the good news is that we've been in this field for a long time, so we have a huge toolbox that we can use of lots of techniques, and you've seen some of them in this session and the previous sessions. And so for many problems that we care about, we can get very nice algorithms. And I've worked on a lot of algorithms like this with these techniques and so on. But for some problems, the best algorithm you can come up with is the so-called exhaustive search algorithm. So for many of the problems that we have, there's a natural search space of solutions. And in fact, for all problems in NP, for example. And now, what you can do is you can just go through this search space and try every possible solution, and then you'll find the answer. This is the exhaustive search algorithm. And even in the 50s, Gödel was very interested in how much, in general, we can improve over the exhaustive search running time for various problems. And to this day, we don't know the answer. For many problems, the exhaustive search runtime for the natural search space defined by the problem is the best we know. And I will call these hard problems. Now, let me expand a little bit on what I mean by a hard problem. So, intuitively, a hard problem is one for which our current techniques don't give us very good runtimes. So these are problems from very diverse areas. And we really want to solve them. So then you take the problem, you look at it, you throw in all the known techniques, and you come up with some algorithm. Okay, you analyze it, and you figure out what its asymptotic runtime is, and you can call it the textbook algorithm because you use the textbook techniques. Now, often these algorithms are exhaustive search. Sometimes they're not quite, but if you look at it, it's like from the side, they're also exhaustive search. So now, these algorithms, unfortunately, often are very slow. And even, remember, we really want to solve these problems, and people have tried for many decades, and even though these algorithms are very simple to come up with, nobody has been able to improve on them significantly. So let me give you 2 examples of this, just so we're on the same page. The first example is the canonical hard problem in computer science. You may have seen it in some of the other talks. This is the Boolean satisfiability problem. In short, it's K-SAT. K is some integer. And you're given, as an input, n variables, x1 to xn, and you're also given a formula. It's a propositional formula in conjunctive normal form, which essentially means it's a big AND of a bunch of clauses. Every clause is an OR of literals, and every literal is just a variable or its negation. So here's an example. You could take x1 or not x2 or x3 and so on. Now this K here in K-SAT is just the maximum length of a clause. So here it's 3. What you want to do is, given such a formula, you want to know if there is some assignment, Boolean assignment to the variable, so that when you plug it in, the formula evaluates to true, to 1. Okay? And the exhaustive search algorithm is, well, there's the search space is the possible Boolean assignments to the variable, so you just try them all. There's 2 to the n of them, because for every variable there's a true or false assignment, and you just try all of them and you plug them in. Okay, and that's roughly 2 to the n times the length of the formula running time. Now, the best known algorithms, unfortunately, look like this. They're 2 to the n with a slight improvement here of minus some constant times n divided by k by some times a polynomial in the number of clauses. Well, this is not very good because as k, the length of the clauses increases, your running time goes to 2 to the n, and that was kind of the silly algorithm that we had in the first place. So you can think of SAT being a hard problem because 2 to the n is very easy to achieve. It's just brute force. But no 2 to the n to the 1 minus epsilon time algorithm is known for any epsilon bigger than 0. OK, so this is SAT. Now, here's one more example. This example is completely different. So here we're given, it's called longest common subsequence, or LCS for short. You're given 2 sequences of n letters over a finite alphabet, let's say A, C, T, G, okay? And we want to know if there's some subsequence that appears in both of these sequences in the same order, and it has maximum length. So, okay? And you can think of this as some sort of sequence alignment problem. You align every letter of the top sequence with a letter of the bottom, and sometimes you can put some gaps, so some symbols are not even aligned, and you count the number of matches. So the blue sequence is the maximum length subsequence over here. This problem comes from lots of applications. For example, in computational biology, you can figure out how similar 2 DNA sequences are. It also comes from spell checkers, because like you type in something, you make a mistake, and you want to figure out the best sentence that actually is the true thing that you meant. Okay, so, and this is solved daily in very huge strings, maybe not the whole human genome, and maybe not exactly this problem, but something that has this at the heart of it. And unfortunately, the best running time for this problem, okay, it's polynomial, but it's n squared, and when n is huge, n squared is not very good. So n squared is a textbook running time. The best algorithm does save a little bit, like log squared of n, but there's still nothing better in the exponent. So there's no n squared to the 1 minus epsilon time algorithm for any epsilon bigger than 0. Okay? And people work on this a lot. We've tried, and we're still stuck. So let me rephrase what I mean by a hard problem. A hard problem is a problem where you come up with some maybe exhaustive search, maybe textbook algorithm that runs in T of n time. N is the size of the input, and T of n is much bigger than n. It's far from what we want. And for many, many decades, people looked at this problem, and they didn't get a t of n to the 1 minus epsilon algorithm for any epsilon. Okay? So there's many examples. And what I want to know is, why are we stuck at such problems? Okay? Are we stuck because of the same reason? Is it the reason that we're stuck on satisfiability, the same reason that we're stuck for longest common subsequence? They're very different. They have very different running times. One is n squared, one is 2 to the n, but they have the same property. People attacked them for many years, and we got stuck at some strange running time. And I want to address this problem, this problem over here. So what I'll tell you in this talk is a way that you can address it, and we will. Okay? All right, so here's the plan for the rest of the talk. I'm going to tell you about some traditional hardness in computational complexity, some approaches that kind of look like they should work, but they don't. And then I'll tell you how to fix them using this fine-grained approach, and then I'll conclude. All right, so let's start with the first one. Traditional hardness in complexity. So here are some theorems that we know, and they're very nice and useful. So for any computational model, nice computational model, you can prove theorems of the following form. There's for every, let's say, constant bigger than 1, c bigger than 1, there exists some problems that are in n to the c time, but they're not in n to the c minus epsilon time for any epsilon bigger than 0. Such theorems, and even much stronger ones, are known. Unfortunately, these problems over here are not the ones that we care about. So for any particular problem like SAT or a longest common subsequence, we do not have the techniques to prove that they're not in n to the c minus epsilon time for some c. And in fact, K-SAT, which we can't even solve faster than 2 to the n time, we cannot prove that it's not in linear time. Okay, there's this huge gap of techniques for us. So we just cannot, for whatever reason, we're unable to prove unconditional lower bounds. Now, there's this other approach in complexity, which comes from the P versus NP problem, which has appeared in many of the talks here. So P is the class of these problems. They return 0 or 1, so they're decision problems. They have an algorithm that runs in polynomial time and the length of the input. And NP is this class of decision problems where if somebody gives you the solution, you can verify it in polynomial time. Now, in P, you have to find the solution, and in NP, you just have to verify it. And somehow, verifying seems so much easier than finding. And because of this, people believe that P is not equal to NP. And there's many other reasons. It's a notoriously hard problem. If you resolve it, you get $1 million. Okay, I don't know if we're into money here, but anyway. So what's important for us is that there's this theorem from the 70s, first by Cook and then by Karp. Cook proved that when k is arbitrary, and Karp proved that for any k at least 3. They showed the following, that K-SAT is NP-hard for every k at least 3. I will explain what this means, but roughly it says that if this problem K-SAT that I defined before has a polynomial time algorithm for some k at least 3, then P equals NP. And we don't believe P equals NP, and maybe that, and this means that, you know, K-SAT requires super polynomial time. For me, you know, what's important for this talk is that this is a sort of conditional hardness. Assuming this conjecture, we get that this problem requires super polynomial time. Okay, so let me delve into it a little bit. So at a high level, NP-hardness has these 3 steps. Really, the only important one is the second one. But basically what happens is first you assume P not equal NP. And then for your particular problem Q, such as SAT, you show that if it had a polynomial time algorithm, you can use this algorithm to solve any problem in NP in polynomial time. And then you conclude, well, because you showed this, Q must require super polynomial time because we assume P is not equal to NP. Okay? Now, a few things to notice. If my problem already had a polynomial time algorithm, it cannot be NP-hard unless P equals NP, because like over here, you already get that every problem in NP would have a polynomial time algorithm, and therefore this assumption is wrong, okay? But I want problems even in n-squared time to be hard, right? So I cannot use NP-hardness to prove that they require n-squared time, because I will be proving P equals NP, and maybe I should be proving P equals NP, but you know, who knows? Now, also, NP-hardness is just too coarse-grained. It only distinguishes between polynomial and superpolynomial. It doesn't distinguish between n-squared and less than n-squared. And I want something that does distinguish between these concrete running times. So, all right. So, okay. So, now, before I continue, I want to just get back to say, why did people really care about polynomial time anyway? Why didn't they just focus on concrete running times as I want to? Okay, so why did they do that? Well, there's a few reasons. Well, you want, whenever you have two efficient algorithms, when you compose them, you want to get an efficient algorithm. Well, you know, if I have a polynomial of a polynomial, that's still a polynomial, so if I call polynomial time efficient, then this works. Another reason is that, remember at the beginning I talked about models of computation, like Turing machines and random access machines. Now there's these theorems that say that you can go between a Turing machine and a random access machine and vice versa by paying a polynomial overhead. And such theorems exist for many models of computation. And because of this overhead, if I only care about polynomial time, I can have model independence. It doesn't matter which model I use. However, even though I said polynomial time is efficient, nobody would say n to the 100 is efficient or even n squared. So polynomial time is efficient only for technical reasons. So now I'll just kind of give up on this polynomial time is efficient, and I will try to build a theory of hardness that kind of mimics NP completeness, but is actually about concrete running times. And we will be able to relate problems with very different running times and still have some sort of equivalences there. Okay. Good. So I finished with this, and so now I'll tell you about the actual approach. And the way I will do it, I will start with NP-hardness, and I'll build on it. So on the left-hand side, I'll have NP-hardness, and then I'll explain what the differences are. All right? So here's again NP-hardness. You had these three steps. There was a hardness assumption. There is some sort of polynomial time reduction that implies that if Q had a polynomial time algorithm, then my hardness hypothesis would be false, and then I conclude that Q must not have one. All right. So in this fine-grained hardness, I will have similar steps. The first step will be I'll have some hardness hypothesis. Now, this hardness hypothesis will be about a concrete running time. So I will pick a hard problem, H, which will be, for example, SAT. And I will pick a function h of n, some time-constructible function, and I would assume my hardness hypothesis will be that h requires h of n time roughly on inputs of size n, but I have to fix my model of computation, for example, a random access machine, because if I don't fix it, you know, anyway. So I fixed my model of computation. And now I have an analog of this reduction type thing. So what I do is I define some notion of fine-grained reduction, which has the following consequence. It says that if some problem Q had better than Q of n runtime, Q of n to the 1 minus epsilon time, then this runtime would imply a better than h of n runtime for my problem h. And then I conclude if the hypothesis is true, then Q must require more than Q of n. It must require Q of n runtime. So this is the difference. Here, I changed my hardness hypothesis to talk about concrete running times. I add a particular model of computation so that this would make sense. Then my reduction also has to be about the same model of computation, and then I have relationships between the running times of the two problems, and then my hardness follows. Okay, so what I'll do next is I will go through all three of these steps, okay, contrasting them with NP-hardness. So I'll start with the hardness hypothesis. In NP-hardness, after Cook's result, we know that the hardness hypothesis is really that SAT requires superpolynomial time. It's equivalent to P not equal NP. And so it's natural to pick SAT as this hard problem H. So, but what should this function be over here? So SAT is conjectured to be really hard, and there's two hypotheses that are already out there since 2001. They're both by Impaliazzo, Paturi, and Zane, and one of them is called the Exponential Time Hypothesis, or ETH. It roughly says that 3-SAT requires exponential time. So there's some deltas, there's the 3-SAT on n variables requires 2 to the delta n time. A much stronger version of this hypothesis says that K-SAT, so for every epsilon there's a K, so the K-SAT requires essentially 2 to the n to the 1 minus epsilon time. In other words, any epsilon that you give me, and you claim that you can solve SAT in 2 to the n to the 1 minus epsilon time, I will produce a clause with K where your algorithm will not work. So this is the strong exponential time hypothesis. So it basically says the SAT requires 2 to the n time. And the brute force, the exhaustive search algorithm, is essentially optimal. All right, so what we'll do is we'll just use one of these hypotheses as our hardness assumption. And I want to point out that both of these are much, much stronger than P not equal NP. P not equal NP just says that requires superpolynomial time. These say exponential time, or even 2 to the n time. So even though they're much stronger, they're extremely believable because we don't have good techniques for these problems. Anyway, good. So on the next slide, I'll kind of list some more problems. They're not very important. All you have to remember is that there are just 3 of them, and they're very simple. They have extremely simple algorithms. So here they are. So let me just quickly go over them. One of them is the threesome problem. Has been studied forever, and all you're given are n numbers. They could be integers, let's say, and you want to know if 3 of these numbers sum to 0. So clearly you can go over to every pair of numbers, there's n squared of them, and check if the negative of their sum is in the set. And if you're careful about how you implement this, you get an n squared time algorithm. There's almost nothing better known, and the hypothesis, which has been around since the early 90s, is that threesome requires essentially n squared time on, let's say, this model of computation. Similar algorithms. So this problem, orthogonal vectors, is, well, you're given a set of n vectors, very small dimension, and they're binary vectors, and all you want to know if 2 of them are orthogonal. You try every pair of vectors, compute the inner product, check if it's 0. That takes n squared times d time, brute force algorithm, nothing very much better known. N squared is essentially the best we know, and the hypothesis is that this requires n squared time. Actually, if you believe the strong exponential time hypothesis, or Ryan Williams showed in 2005, that you should definitely believe this one, because if you can solve orthogonal vectors faster, you can also solve SAT faster. So this one's very believable. Finally, there's this other graph problem. You're given a graph on n vertices, it has polynomial weights on the edges, and you want to compute all the distances between every pair of nodes. And there's these classical algorithms that run in n cubed time. In fact, if you massage the problem a little bit, these algorithms are also kind of brute force. There's also exhaustive search, and there's this hypothesis that this problem requires n cubed time because the best known algorithms are also essentially n cubed. So anyway, so there's these 3 very simple combinatorial problems from different areas of computer science. They have been attacked for many years, and these are the best running times, and we have hypotheses from them. And these are the hypotheses we'll use for various reasons. You can ask, why 3? Why don't you just pick 1? Okay? This is a very, very valid question. Actually, well, that's the answer, I guess. What happened? Well, the answer is there's reasons why they're not equivalent. Okay, good. Thank you. All right, so there's some strengthening of this hypothesis, of the strong exponential time hypothesis, which may or may not be true, but current techniques don't allow us to disprove it. So if you believe this, it suggests that these cannot be equivalent. So if we really want to understand the space of problems, we should probably consider more than one problem, and let's consider these. All right, so what we did so far is I took this hardness hypothesis and I showed you some hypotheses you can use. Now, the next thing I do is I will show you what a fine-grained reduction is, and this will be the most technical part of this talk, so bear with me. The first thing I'll do is I'll recall the various reduction concepts that people have used in NP-hardness, and then we'll build on them. So the polynomial time reduction that is used in NP-hardness is something called a many-one reduction. It basically looks like this. Given an input of a problem A, so A and B are some decision problems. They can take bit strings to 0, 1. And what a polynomial many-one reduction is, it's some algorithm that runs a polynomial time. It takes any instance of A, produces an instance of B that could be polynomially larger, and then the answers to A and B, to those two instances, have to be the same. If this one, the answer is yes, then so is this one, and so on. So this immediately has various useful properties. For example, if B has a polynomial time algorithm, you can also solve A by composing the reduction with the algorithm on B and returning the same answer. However, this is a very restricted type of reduction because you only produce one single instance and your answer has to be exactly the same. And for example, if I wanted to take a problem where the range is like more than 1 bit, so let's say I'm computing n-squared distances in a graph, there's no way to use this reduction to reduce it to a decision problem where the answer is yes or no, just because the decision problem only gives you 1 bit as an answer, and if your reduction is like very, very fast, there's no way you could get the n-squared or more bits for the original problem. So this is very restricted. Also, for my purposes, it's not very useful because it only talks about polynomial time. There's many polynomials. And what about non-polynomials? What about n to the log n and so on? This is not captured here. N squared versus n cubed is not captured, so it's very coarse-grained. Now, there's this other type of reduction, which is better. It fixes one of the problems. It's called a Turing Reduction. And now the picture is like this. You're given an instance of problem A. A Turing Reduction is some polynomial time algorithm, which has oracle access to problem B. So what this means is that this algorithm comes along and starts producing instances of problem B, and some magical entity, the oracle, gives you answers back to the problem B, and then you solve the instance of problem A. This is what Turing reduction looks like. Now, it has the same nice properties. So if you could solve B in polynomial time, because the instances here have polynomial size, polynomial is a polynomial, you immediately use this algorithm, the reduction, to solve instances of problem A in polynomial time. So there's all sorts of other nice properties. The reason why it's not used is for this technical reason that it doesn't distinguish between NP and co-NP, but I don't care, right? I care about running times. I don't care about P versus co-NP right now. So, so this is really good for me, but it's still coarse-grained. It only cares about polynomials. And I want to talk about concrete runtimes. So what I'm going to do is I'm going to take this sort of type of reduction and transform it a little bit. So here is the notion of fine-grained reduction that we came up with in 2010. Now, you have two problems A and B, and the intuition is you have, let's say, their textbook running times are A of n and B of n, and I want my reduction to have the property that if B has a better than B of n time algorithm, then A has a better than A of n time algorithm. So here's how we do it. let A and B be the problems. Little a and little b are their running times, the time constructible. And we say that A is AB reducible to B, this technical thing. So for every epsilon, there's some delta, and an A of n to the 1 minus delta time algorithm, better than A of n algorithm, that can solve A on instances of size n by making these oracle calls again to B with this interesting inequality. So let me parse this for you, okay? The whole reason to have this is so that I can show this proposition. Proposition is that if A is AB reducible to B, and B is in faster than B of n time for some B of n to the 1 minus epsilon for epsilon bigger than 0, then I get an A of n to the 1 minus delta algorithm for A for some delta that's also bigger than 0. And so the way you prove this proposition, given that this definition, is as follows. Well, suppose B had a B of n to the 1 minus epsilon algorithm, and the reduction produced these instances of sizes n1 to nk. Now what I can do is I run the reduction and then run the algorithm for B here instead of the oracle, right? And the runtime for running the algorithm over here is this sum. The sum over I of B of n sub I to the 1 minus epsilon, because I had this algorithm over here. Now because of this inequality from my definition, I see that this running time to run the algorithm on the instances over here is at most A of n to the 1 minus delta. And composing it with the actual running time of the algorithm, I get A of n to the 1 minus delta plus order of that, and therefore I get my proposition that if I had a good runtime for B, then I get an improved runtime for A as well. Okay, so this is the main definition that we have, and we have many, many examples of how to produce such fine-grained reductions for many problems, as we'll show you in a bit. All right, another very simple proposition to prove. I know you can't see it, so I'll just say it. It's transitivity. If A is AB reducible to B and B is BC reducible to C, then A is AC reducible to C. So something that you want to have, and it allows you to compose these reductions with each other. All right, so this is the type of reduction we use. All right. So what I've done so far is give you the hypothesis, I define the fine-grained reduction, and now I'll show you what we know about what you can prove. So the reason why NP completeness became so popular is because of Karp's result in 1972. So Cook had shown that SAT if you had a fast algorithm for it, you can solve everything in NP fast. But Karp showed that this holds for many, many problems. So he took SAT and reduced it to many very diverse problems, 21, but if you're very careful, you'll count and you'll see that there are not 21 here. There's a reason for that, namely that this problem it's both undirected and directed version are there. But anyway, so Karp showed that there's 21 problems that are all equivalent and they're all in NP, and people from many very diverse areas worked on them and couldn't get a polynomial time algorithm for them. And this made people think, well, they must all be hard. Now, are we all negative here? Maybe we are. But you could also think of it from a positive point of view. There's all these problems. We have many different techniques. Maybe some new technique will work on one of them. And then you've solved all of them. So this is beautiful. And this is why NP completeness is interesting. And also, you can also show hardness for problems that are not in NP, like quantified Boolean formulas and so on. So this theory has many diverse applications, and then many, many NP-complete problems have been found since then. Now, fine-grained complexity, the area that we're working in, is still in the beginning stages, but we already know quite a bit. So here's what we know. So we have these 3 or 4 problems that I defined earlier, and it turns out that you can use fine-grained reductions to show that just these hypotheses about these 3 problems show that the known algorithms for many, many, many problems are optimal if you assume these hypotheses. They're really, really tight. For example, this longest common subsequence problem, if you solve it faster than n squared time, like in n to the 1.99999 time, then this orthogonal vectors problem would be in faster than n squared time, and the strong exponential time hypothesis will be false. So this is something we showed in 2015. And there's many other problems like computing the diameter of a graph and so on. So for threesome, people worked on this problem in the 90s, and there was a paper that showed that if you believe threesome requires n squared time, that all these problems in computational geometry also require n squared time. And then it was a very nice result, and it spawned many other papers, but it was really constrained to computational geometry. And what we did was we thought, well, why not add it and add problems that are not in geometry? So we started showing that the threesome conjecture shows that various sequence similarity problems and so on also have tight algorithms. And this is kind of growing. But the most interesting thing to me over here is that we have an equivalence class. So over here, the all pair shortest path problem has a lot of problems in graphs that are actually n cubed equivalent to it. And these problems are very simple to state. For example, if you're given a graph, dense graph, let's say, and I want to compute its radius, okay? Or I want to compute, you're given a graph and two nodes, S and T, and I don't want to compute the shortest path between them, but the second shortest path. Okay, the second shortest path means like you have a sorted list of the shortest paths and you find the second one. So this problem, it turns out, is n cubed equivalent to all pair shortest paths, even though computing the shortest paths is very simple, very easy. Anyway, so in the next slide, which is the next to last slide, I will show you an example theorem. I won't prove it to you, but here it is. The sample theorem is like this. You're given all pair shortest paths is equivalent to a negative triangle. What is negative triangle? So negative triangle is this following very silly problem. You're given a graph on n nodes, and you want to know if there's a triple of vertices such that the weights on the edges between them sum to a negative number. Okay? Is there a triple of vertices? Well, I can try all triples of vertices. This takes n cubed time, and I can check the condition. But doing anything polynomially better would resolve this all pair shortest path conjecture, and so on. Now, maybe you don't like graphs, so let me rephrase it in terms of matrices, okay? Here are the problems in terms of matrices. It turns out that the all pair shortest path problem is equivalent to the following problem, which is the computing the matrix product of two matrices over the min plus semi-ring. In other words, you're given matrices A and B, n by n. Their entries are integers between 1 and some polynomial in n, and you want to compute for every ij the minimum over k of aik plus bkj. Min plus matrix product. Turns out to be equivalent, and n cubed is the exhaustive search runtime. Over here is the trace of the cube of a matrix in the min plus semi-ring. So you're given n by n matrix, again integer entries, and you want to compute the minimum of over ijk of aij plus ajk plus aki, and in particular, in fact, you only care about whether it is negative or not. Okay? So it turns out that they're equivalent. And the way we do it is we give a very specialized fine-grained reduction that actually produces many instances of this problem given this one. The other direction is easy. All right. So how much time? Well, I'll be even faster. All right. So I will just conclude. Oh. Before I conclude, let me, somebody told me that every talk that's really good has to have an open question. Now, I think that, okay, I can always say resolve P not equal NP, okay, that's kind of a, everybody says that. So just what you gotta do is give me a subcubic algorithm for this problem, or this one. Okay, just a 2.9, into the 2.99 algorithm. And I'll be happy because then this class will all have non-trivial algorithms. And I think this will be very cool, and one of the nice things about having equivalences is that they go both ways. Either the problems are all hard or they're all easy, so if you give me an algorithm, I'll be perfectly happy. If you give me an unconditional or lower bound for one of these problems, I'll be also super happy. But, you know, we'll see. All right, so that's my open problem. Now, in conclusion, since we defined this concept in 2010, there was an explosion of results, not only by my group, but many other groups, and people did lots of things. They added more problems to the picture. They tried to strengthen the hardness hypothesis. They tried to replace them with a single hypothesis. They gave connections to other areas of complexity, and so on. And recently, the fine-grained idea has spread all over the place. So now we have, here I showed you how you can look at just running time, but you could have these reductions when you focus on space. So there's fine-grained space complexity. You can care about the approximations. Here I only talked about how you can solve problems exactly, but maybe you want to add approximability to the picture, and people have done that. You can look at other models of computation, like we had a paper on the I/O model of computation, and there you can build a theory as well. There's various data structure variants of these ideas. Now there's this new idea of having fine-grained cryptography, where instead of having these assumptions that are about exponential time running times, we now have assumptions about average case instances and how you can solve them. You cannot solve them in faster than n cubed time, let's say, and so on. And what's interesting is, like, I'm very excited to see what's next. So if you have some idea where you can replace something where somebody talked about polynomial time or something like this, just replace it with concrete running times, and that will be very interesting to me. Anyway, so look at my survey. I wrote one for the proceedings here. It's very nice. Send me an email if something is interesting. Anyway, thank you.
I have an idea. It seems that you are now planning to make the polynomial hierarchy in problems that can be solved in n cubed time and no less and so on. So why don't you put up $1 million for somebody showing there's no algorithm for all shortest path that is faster than n cubed? That would be the real thrill, I think, and people would jump into the area.
Give me the $1 million. Okay, I'll totally do it.
Let me the $1 million in your price range. That's just.
All right, I'll give you $100.
That would be interesting to see whether people get excited about it. Okay. Yeah. So, do you believe there is no algorithm faster than n cubed for all shortest paths?
I don't believe that, but. I do think that orthogonal vectors, though, that one might require n squared time.
What about matrix multiplication?
Oh, that's one of my favorite problems.
Okay, yeah. Where is that? Well,
right now, the exponent is like, okay, matrix multiplication and n by n matrices. Right now, the exponent is like 2.3728 something, anyway. Yeah. Anyway, so people believe it should be n squared. Right? This would be an optimal algorithm because n squared is the size of the input, so it's really order n. Now, I would love to have this algorithm. This algorithm would make everything beautiful. There's all these reductions that show if you had an n squared algorithm, then you have an n to the 2.5 algorithm here, n to the whatever. It's all very beautiful. The theory is wonderful. Unfortunately, we're not there. In fact, unfortunately, I start proving these theorems that no known techniques can give you n squared, and it's very sad. But I would like to have the opposite. But unfortunately, this is what the truth is. There are no techniques will not get us there. But there will be new techniques.
Okay. Are there other questions?
So, you say that this is about concrete running times, and so I would like to know to what extent this models the complexity of actual algorithms that you can run on a computer.
Okay. All right, this is a very good question. So we're in the beginning, right? And the way I've defined fine-grainedness is between T of n and T of n to the 0.999, right? That's where I'm differentiating. Now, on real computers, maybe you want to have a better model of computation first, okay? So you fix something else, but also you might care about the constant, right? You might care about polylogs, right? So right now we're fine-grained, then you're going to get finer-grained, finest-grained, and so on.
For instance, for matrix multiplication, what would the exponent in practice be for you?
Oh, that's a wonderful question. There's all sorts of approaches to this. There's some not very well-defined approaches, like you can say combinatorial algorithms, whatever that means simple algorithms and so on. So then you restrict yourself to this type of algorithm, or you can define a notion of the exponent for practical algorithms where you actually care about the constant in front of the runtime and so on. There's various ways to approach this, and we're still in the beginning stages, but we're thinking about it. So, yeah.
More questions? Okay.
Is there something special about integer exponents in the algorithms that you considered? For instance, matrix multiplication could be 2.25. It doesn't have to be an integer. Could you say something about concrete running times versus integer exponents?
Oh, yes, integer exponents. So we're not restricting ourselves to integer exponents, as you see, but yeah, I don't yet understand what's going on. There's these problems where the exponents are like 2.5, and you can tie them in over here. I don't know what makes it like, okay, so I think probably what's going on is that these problems are equivalent to something where the brute force running time there is that exactly. For matrix multiplication, it's different. So as you know, there's the rank question, so it's a little bit different.
Okay, I see no more hand. Let's thank again for a wonderful presentation.
Thank you.